Hi, my name is Jamie DeYoung, and I created this video, the sum of the first n numbers, for the course MAT136 at UTM. So the goal of this video is to prove that for all positive integers n, the sum of the first n positive integers is n times n plus 1 divided by 2. And first, we're going to look briefly at how this works. Why does it make sense? And after we've done that, we'll write a proof using sigma notation. So what we'll do is we'll draw, first of all, the first n integers. So we'll draw 1 dot, then 2, then 3, then 4. Now I stopped at 5 because of course I can't draw too many in the picture, but imagine this goes up to n. And this forms a triangle shape. It's n across and n high, and the sum of the first n numbers is the same as the number of dots. What we'll do after that is we'll actually draw another copy of this, upside down and reversed, on top of the first lot. So this is also n by n. It makes the sum of the first n numbers if you add up all of the red dots. And we've just put this on top of the first lot to make a rectangle. Why does this help? Well, the number of dots in total is 2 times the sum of the first n numbers, because we've drawn 2 copies of it. And it's also a rectangle, which makes it relatively straightforward to count how many dots there are. So let's do that. We know it's n across, and we know the height of the blue dots is n, but there's one more because there's one that's red, so the total height of this rectangle is n plus 1. So that means the number of dots, which is twice the number we're looking for, is n times n plus 1. And that means the number we're looking for, the sum of the first n numbers, is half the dots, which is a half n times n plus 1. So that's a pictorial representation of what we're doing. Now let's try and do that with numbers. So we'll write down the numbers from 1 to n. That's the numbers we'd like to add up. And then, like we did with the dots, we'll write a second copy of this, but we'll do it the opposite way around. So each of these columns in this representation is kind of like the columns of dots. There's one blue and n red ones in the first column, for example. And then what we'd like to do is add all of these up. So we're adding 2 copies of the numbers 1 up to n. And each column gives us n plus 1. N plus 1, and then n minus 1 plus 2 is still n plus 1. And this is the same for all of the columns. So each column is n plus 1, and there are n columns. So that means when we add up 2 copies of each of these numbers, we get n times n plus 1. And as we saw in the previous representation, we divide this by 2 to get the sum we're actually looking for, and that gives us n times n plus 1 divided by 2. So that's why this makes sense. Now, we'd like to actually write a proof of it, and you've been learning sigma notation, so we'd like to do that using sigma notation. So the theorem we're looking to prove is that for all positive integers, n, if we add up the first n numbers, we get n times n plus 1 over 2. Now, if we'd like to write a proof using sigma notation, we'd probably like to actually also write the theorem using sigma notation. So we'll rewrite this sum of the first n positive integers as the sum from I equals 1 up to n of I. So this says exactly the same thing, we're just writing it with sigma notation. Okay, now we would like to actually prove it. So this sum that we're interested in, we'll call it S. And what we did before is we said we'll take 2 copies of those numbers. So we're interested in 2S, which is the sum plus another copy of the same sum. Now, when we did this before, we actually wrote the second set of numbers in reverse. So instead of I, we're actually interested in something perhaps a bit like n minus I. Now, n minus I, when, for example, I is n, would give 0. And 0 isn't one of the numbers we're looking for. It's a bit too low. And when I is 1, we'd get n minus 1. We'd actually like to go all the way up to n. So it's not quite n minus I, it's actually going to be n minus I plus 1. So instead of this same sum for the second one, we'll replace it with the sum from I equals 1 up to n of n minus I plus 1. And if you're not fully convinced that that is the same sum as in the first line, then write down all the numbers in it for some small value of n, just to check that they are in fact the same thing. So now we have two sums with the same indices, so we can combine them together. So we get the sum from I equals 1 up to n of I plus n minus I plus 1. So that's just combining the two sums into one. Now we have I and minus I, so those cancel out to leave us with the sum from I equals 1 to n of n plus 1. Now, n plus 1 isn't actually dependent on I at all. That means we can bring it outside the sum, leaving us with n plus 1 times the sum from I equals 1 up to n of 1. Now, that is just essentially taking the sum of 1 plus 1 plus 1 plus 1 n times. And if we add 1 together n times, we just get n. So this is n times n plus 1. Now, we've calculated 2s. What we're actually interested in is s. So we now divide this by 2. So we get s equals n times n plus 1 divided by 2. And s was the sum we're looking for. So that gives us a proof of this property. Now, you might ask, what about other values? So instead of adding the first n numbers, perhaps we could add their squares or their cubes. Why can't we do that? Well, we can. The proofs are a little bit more complicated, so we're not going to be looking into those in detail right now. But we do have expressions for the sum of the first n squares and the sum of the first n cubes, and so on. So I've got those expressions here, and you can use them, we just won't be proving them. Okay, so I'm going to leave you with a few exercises that use these formulae. The final answers are on Quercus if you would like to have a look at them, and if you have any questions about the process for solving these problems, come and talk to me in my office hours, or you can ask on Piazza. Thank you.